In this tutorial, you'll learn how to optimize a model's parameters to fit user-supplied data. For this example, we have a simple model from closed and open states and transition rates between them. The opening rate depends on the concentration of some drug. And the protocol that we're simulating the model's behavior for is a whole family of drug pulses, shown here in green, of varying amplitudes. And we see the simulated probabilities in the open, shown in red, and the closed states, shown in blue, to each of these drug pulses. And we can view them individually or all together. In addition, for this protocol, we've defined a summary of the model's maximum open probability versus the amplitude of the drug pulse, and that's shown on the lower plot below here. Now, for this example, let's say that we have some experimental data for the probability in the open state for each of these drug pulses, and or we have data telling us the maximum open probability versus a drug amplitude curve. And we'd like to optimize the parameters in our model to fit that data that we've got. So for this example, we'll actually use some of our simulations to generate this fake experimental data and then fit our model to it. So to do that, first, let's only look at the data we're going to be interested in, and that is the probability in the open state. So on our y-axis here, instead of looking at all the states, we'll only look at the open state. We'll also remove the stimuli. So all we're seeing is the series of open state probability curves for our simulation. And then let's just switch to a Monte Carlo simulation style, just so it looks a little more like real data. And then we'll export this as just tab delimited column data text file by selecting Export Visible to Text. And I'll just call this open.txt and save it. And I actually already have one. I'll just replace it. And we'll also save our summary response by analogously exporting that to text file. And I'm going to name it popen, which is the name of the summary in this particular case. Place that. Okay, we can take a look at those files quickly. So the open data is a series of text columns, and in this case they're alternating x, y, time, and the open probability. And we have a pair of columns for each subsequent simulation in the entire family. The data files that Kinetic Model Builder can read and write are all simple text files that are tab delimited column data text files, and it doesn't understand any sort of formatting. So if you want to load a file in, say that you exported from Excel, you might need to strip any non-plain text characters that it has in there. So you just want to be careful about that. It doesn't matter if you have successive XY columns or simply one X column and then subsequent Y columns. What happens is the program will parse the first row for the column titles, and it'll decide what format it's in, and then we'll parse the data based on that. The popen file is much more simple. It's just two columns, max drug versus our popen summary. Okay, so let's see, let's go back to our program. Here we go. So now let's go ahead and switch back to our eigensolver method. So our simulations will look smooth, and then let's load in the data that we just exported as if it was actual experimental data that we'd like to fit our model to. So to do that, in the protocol toolbar, we click Info, and then go to the Reference Data tab, and let's add two different reference data objects. One will be for our open probability and one for our popen summary. Now the important thing about the reference data is that its name has to match exactly the name of a signal that it's going to be matched to. So in this case, the name could be the name of a state group, of a summary, or some of the special reserved names such as current, gating current, or user. So in this case, let's give it the same name as our open state, and now it'll refer to the probability in the open state. And for this one, let's name it popen, which is the name of our summary. So it'll now refer to this summary. And to load the data file, we'll simply double click in this box, go find it, and there we have it. Let's load this one. Popen, great. Okay, now we won't see any reference data until we rerun the simulation. There we go. So now we can see in blue our simulated response, and in gray our reference data, which is our fake experimental data that we just exported. And the same we can see for our summary. The reference data that gets loaded into the simulation is actually sort of sampled and interpolated from whatever reference data you load. So you can load reference data with a much higher sampling rate than your actual simulation, and that data will be downsampled and interpolated to match the sample points in your simulation. Okay, so now let's go back to our model, and so right now it obviously fits the data really well, but let's make it not fit the data so well. So let's take our opening rate, and instead of 1, let's make it 100 per second. So we'll go ahead and simulate that, and now we can see that our model is opening much faster than our data suggests it should. So we'd like to optimize the model to fit this data to recover our original opening rate, which was 1 per second. So to do that, let's go back to the model again, and the opening rate, K0, is, we're just going to optimize one parameter for now, but you can do as many as you want. And we're going to go down to where it says fix K0. And we need to uncheck this to allow this variable to vary during optimization. And it will vary in between these bounds. So let's even make them a little bigger, just for, doesn't really matter for now. Okay, so now during the optimization, K0 can vary between these two values, and it will attempt to minimize the weighted sum of squared errors across all the sample points in each of these series of simulations, as well as the summary. So to run an optimization, we just click the Fit button up in the toolbar, or we can select Model Fit, and it will run a simplex iterative fit for the specified number of iterations, in this case 100, which should be enough for just optimizing one variable. So we'll just click Fit, and it finished. Sometimes you just need to click here to refresh. There we have it. So it did a really good job of recovering. The original almost got the rate to be 1, which was the original rate, based on the data that we fed it in. So in essence, that's it for optimizing your model. There's a couple of additional tweaks that I'll explain about various parameters that you can do. So the first thing is about weighting. So you can weight the fit for sample points non-uniformly. And the way that that's done is to go into the Info tab here for the protocol and come down to this option here, which says epoch exponential weight amplitude. In this case, actually, it was already turned on. So if this was 0, we would have no exponential weighting. So when it's 1, what this means is that all of the sample points will have sort of a constant weight factor supplied to them for fits, and that's given by this parameter here. And in addition to that, we can add an exponential weight across sample points, which will have the given amplitude and the given time constant, and it's repeated for each epoch in the simulation. So in our case, where we have a single square drug pulse, we actually have 3 epochs. We have the epoch prior to the drug pulse, the epoch during the drug pulse, and then the epoch following the drug pulse. So we'll leave that on. I'll just re-simulate it to make sure it's been calculated. And now let's actually take a look at that. So let's see here. Instead of viewing our open state, we'll view all of the state signals together, and we'll also view the weighting that is being applied. So now, instead of a flat uniform rate of 1 across all the sample points, it's giving an exponential weight for each epoch. We see the epoch prior to the pulse, the epoch during the pulse, and the epoch following the pulse. And often it's the case that this very first epoch just is baseline and you're not interested in weighting the points differently there. So you have the option of ignoring that first epoch for the weighting. And if we resimulate that, we will now see there's uniform weight there and exponential weight on the next two epochs. And this is simply useful for weighting fits to very, very fast changing signals, more than sort of baseline where your signal is not changing very much. Okay, so that is the exponential weighting. We can go back, look at our open state probability. Okay, so the other options you have for reference data are, there's a couple of them. So the first thing you can do is you can actually shift your reference data in time without sort of reloading a whole file. You can just apply a shift here. You can also normalize it and then scale it. And this is just sometimes very useful, but those are all self-explanatory. You can also give each reference data its own weight, and that means you can weight the fit between different signals within the same protocol differently. This will be explained in a different tutorial. And then finally, we have our first row and first column. And so for every simulation that's done, you're actually doing a m by n matrix of different simulations for each of the m by n unique stimulus conditions that are specified. So in this particular protocol, we have actually defined a whole series. In this case, I think there's 15 different columns along the simulation matrix, and we can step between them like this, and you can see that there's reference data associated with each of them. And the first column parameter here actually specifies, when we load in a data file with a whole series of XY data columns, it specifies what simulation along that column that we should start applying that reference data to. So if instead we just change this, say, to 2, and now rerun our simulation to update everything, if we go to the very first column, we see our simulation but no reference data. And now the reference data actually starts on the second simulation sweep. And of course, it's not matched anymore because this one really should be for the first one, and so forth. So let's just go put that back on the first column. And then the other option we have is to specify the row that we'd like our reference data to be applied to. So right now in this particular simulation, there's one row with 15 different columns. And here we're stepping through the various columns. So let's add some stimuli to add a row. So if we go to our stimuli, we have our drug pulse specifying 15 columns of different simulations. And now we'll add a different drug, drug B, say. It has no relevance to our model, but it'll, just because it's there, it will add rows. In this case, we give it 2 values separated by a semicolon. So now we have 2 rows and 15 columns of stimulus conditions. And if we simulate them, we now have boxes for step through our rows and to step through our columns. So if we look at the first row, we see all of our 15 columns, and we can step through them all or look at them, and they all have reference data. But our second row, we have the exact same simulation, but no reference data. And if we go into our reference data here and choose the first row to be 2 and resimulate this, now the reference data is associated with row 2 and not row 1. So essentially this allows you to sort of place what portions of your various stimulus conditions your reference data is assigned to, and very easily. Okay, I think, yeah, one last thing for optimizing the model is sometimes you have sort of spurious artifactual signals in your data that you've loaded in that you don't want the model to try and fit. And so you can exclude regions from fit simply by adding as many regions you'd like, specifying start and durations. And these parameters can be given sort of a whole n by n matrix of parameters just like you would for stimuli. And these will specify regions that will be excluded from the fit. Okay, that's it on optimizing a model, and good luck.